Okay, ladies and gentlemen, let's dive into the session 15 on reinforcement learning. Can we all please join our hands together to welcome Dr. Manoj Shakya.
Good morning, everyone. Thank you for having me here. I really appreciate that even this Saturday morning, it's very chilling outside. Many of you are here listening to my lecture, and I really appreciate that part. But today I'm talking about reinforcement learning and reinforcement learning from human feedback, basically. So my name is Manoj Shakya. I'm an assistant professor at the Department of Computer Science and Engineering, Kathmandu University. I recently completed my PhD from Nanyang Technological University, Singapore. And during my PhD journey, I actually worked in this field, reinforcement learning. But I'm not talking about my work today, but basically the basic concepts, very basic concepts of reinforcement learning. Because I'm pretty much sure that in our curriculum, basically in Nepal, many universities and many colleges, they offer artificial intelligence program, but they do not have reinforcement learning as a subject in the curriculum. So I'll be talking about reinforcement learning, the basics of reinforcement learning, and along with that, I will also discuss about the reinforcement learning from human feedback, and this RLHF kind of thing is really popular these days. Yeah, and in today's talk, let me give you the outline. So after the lecture, we are going to have the QA session as well. So without further ado, I quickly dive into the content itself. Okay. So the first part, I will discuss about what is actually the reinforcement learning. So giving you the overview of reinforcement learning. And there is this mathematical formulation of a reinforcement learning problem that we call it Markov decision process. So in my lecture, in today's lecture, I will also talk about what is MDPs and how actually we design MDPs. So basically my lecture will inspire many students. I think most of you are already, if I am correct, many of you are students, belong to some universities or colleges. So today I will also discuss about Markov decision process, so-called MDPs, and we'll see how MDP and reinforcement learning, they are closely related, how they are related. And I'm going to talk about some core concepts of reinforcement learning. For example, value functions and what is actually Bellman equation and exploration versus exploitation. These are some of the terms and terminologies I think people like us should be aware of. Because when somebody talks about reinforcement learning, if I am, for example, if I know something about reinforcement learning, I know these kind of words. For example, what is state value, what is action value, what is Bellman equation, and then what is exploration and exploitation, what is the trade-off between these two things. So if I am aware of all some basic concepts, these core concepts of reinforcement learning, then I feel like, okay, I can now really work on problem that can be solved using reinforcement learning. But I will also talk a little bit about, just give you a very small information about Q learning algorithm, because there are so many RL algorithms, and one of the most popular algorithms in RL is Q learning algorithm. There are like tons and tons of algorithms right now. For example, DQN, PPO, double Q, DQN, and many algorithms, popular algorithms are there. But I will just give you a very brief information about Q learning algorithm. And of course, I shall not skip this topic as well, so-called deep reinforcement learning. But my topic definitely is about reinforcement learning. But then again, I thought, like, why not I give a very short, brief introduction about deep reinforcement learning. Of course, by name itself, we can guess like it is the combination of deep learning and deep reinforcement learning. When we combine them together, that becomes a deep reinforcement learning. But what actually it is, what does the combination actually mean to us? We'll talk about that later. And then there are a couple of slides I have regarding this reinforcement learning from human feedback. This is what we call RLHF in short, and it's really, really getting popular. And again, there's this chat GPT. That's why this RLHF is really getting popular. I'm really sorry about my voice. My voice is not like this actually. I'm really, under medication, and then, well, so next time if you meet me and if you talk to me, you'll find my voice different than what you are listening actually. Yeah, I'm really sorry for that. So, and then finally, the QA session is always there. So basically, I list down some of the learning objectives of today's lecture. One is to understand the fundamentals of reinforcement learning, and we get familiarized with MDPs, and we know what Bellman equation is and how important this equation is, and the basics of reinforcement learning from human feedback. So now let me start reinforcement learning, what it is actually. I can see many of you from here. I think even if you can raise your hands, I can probably even count. How many of you are familiar with this equation? For me, it's like E equals mc squared. For me, it's a very magical equation. So how many of you have seen this equation before? Let me see your hand. Okay. Good. Thank you so much. I can see many students, many participants raising their hands. Thank you so much. Okay. Well, this is what we call a Bellman equation for Q value function. We have to keep in mind this is for the Q value function, but we'll come later on what this Q value function actually is. In this talk, basically, I will at the end, I will come to this equation later on. We will see each and every part. What is this gamma actually mean? This max, Q, S prime, A prime, S, A. What is this? Each component we'll come to know later on. But before that, we derive that Bellman equation. We need to understand why this RL is so powerful, and then what are some applications of this reinforcement learning. So if you look at this one, I think many of you have already seen the movie, not the movie, but the documentary, is so-called AlphaGo, right? So AlphaGo is a reinforcement learning agent. I consider that one. AlphaGo is a reinforcement learning agent where AlphaGo was supposed to compete with this champion from South Korea. His name is Mr. Sidol, I think. Yeah, he is actually a champion of this game called Go. And AlphaGo was trained very well. I think, David Silver was one of the core team members who developed this AlphaGo concept. So this AlphaGo was actually designed using the RL algorithms, and then they came to the point that, okay, let's compete this one AlphaGo with this champion, and then finally out of 5 games, AlphaGo won 4 rounds with this champion. So with this, from this point, I think real reinforcement learning really get a very high pace. I mean, it's getting really popular, and people are really like into this RL algorithm, and we have a feeling that RL algorithm can be a very good option, because when we think of RL reinforcement learning, how do I categorize basically is, let's suppose that this artificial intelligence is a superset, okay? Within this artificial intelligence, we have another set, we call it machine learning. So, and then within this machine learning itself, we have like different mechanisms, different paradigms. And one of them is probably you are very familiar with that. That is what we call supervised learning. And there is another so-called unsupervised learning. And there is this third one, very competitive to all those things, but totally different from supervised and unsupervised. And what we call, that we call it reinforcement learning. So supervised learning, unsupervised learning, and reinforcement learning. We use all these paradigms to train the machine. Basically, we train the machine via supervised, via unsupervised, and via reinforcement learning. But this time, we are talking about reinforcement learning. So, let me give you one more example. This one is a very great example again. You'll see so many games out here. These are all games related to Atari games. So Atari games, actually there was this paper related to deep reinforcement learning. So they developed this reinforcement learning RL algorithms to play all these games. So when human play these games, they definitely we score certain we score certain marks, and RL algorithms also play RL agent also play these games and they score certain marks. But what we found is that RL algorithms scored more than what people can score, what human can score. So with this example also we can say that RL algorithms are really getting better in terms of playing games. But then again, with these two examples, what I'm trying to say is supervised learning is one paradigm which is very, very different than this RL concept. How RL actually train the agent is different than how supervised learning actually works, how unsupervised learning actually works. So RL, how it does actually is via trial and error concept. So in our reinforcement learning, we have this word called trial and error. So we try something, right? We try something and we get the result. The result is either negative or positive. That means the environment will tell you like, you did very good. Or the environment will tell you, you did very bad in this. I mean, the action that you took is really not good. So with the interaction with the environment, the agent is actually learning something. That is what we call this, that is how RL algorithm actually works. I mean, RL actually works. So looking at these two examples, what I'm really trying to say here is RL algorithm has different mechanisms, and it is really different than how supervised and unsupervised algorithms work. So we keep in mind that RL actually is a different paradigm, okay, a different paradigm. But how actually it works, we'll come to the point. And I'm going to give you one more example here. This is actually how ChatGPT actually is working. I mean, using reinforcement learning. Basically, ChatGPT is using reinforcement learning as a reinforcement learning from human feedback. To get the feedback from, ChatGPT basically gets the feedback from human, and with that feedback, ChatGPT is actually enhancing the performance of ChatGPT itself. Okay, and we will later we will talk more about this part also. So these are some of the examples where reinforcement learning is really doing a great job. So with these examples, what I really want to really the message is that reinforcement learning has many applications in all these areas. For example, if you think of drone, or if you think of a robot that works in the agriculture field, or if you think of a robot that works in probably hotel or even in the industries, you can make use of reinforcement learning. You know why? Because reinforcement learning, RL in short, is actually good in making a sequential decision. This is the word that I really want to introduce. Please, if you are jotting down something, you jot down this word also. Making sequential decision-making problem. Sequential decision-making. So RL is found to be very good in sequential decision-making problem. For example, even if you see this game, or even if you see all these games, not only these games, but other examples also, if there is a sequence of making decisions, you make decision, you get something, and you move on. You make decision at this point, you get something, and you move on. Right? So if the problem is something similar to this part, then you can think of RL as a solution. That's the main message that I really want to give with this slide. But then let's dive into the skeleton of reinforcement learning. In reinforcement learning, there are two components. They interact together. One is what we call agent. Here is the agent, and the other one is the environment. So, environment actually provides the state information or the observation, let's say, to the agent. So, agent receives all the informations. What is the status of the current situation from the environment? So, once the agent receives the state or the information from the environment, the agent then takes an action. It decides which action to be taken. The agent decides which action to be taken. So, and this action actually impacts the environment. And environment actually, if you look into the environment, then there is a change in the state. Why there is a change in the state of this environment? Because there is an action there. The action performed by the agent actually changes the state of the environment. And based on the change in the environment, this environment actually provides reward to the agent. Now, this is the complete skeleton of a very standard reinforcement learning, kind of thing. So, now look at this one. This diagram is a very standard diagram, okay? That's why I'm actually explaining this one a little bit more. So, why agent takes certain action is actually based on the reward itself. So this reward is very, very important. But in general, what do you call it? Reward is basically, okay, you are doing good. That is again a reward. If somebody says you are not doing good, that is also a reward. Okay? But reward is, in the context of RL, this reward is a scalar value. Probably 1, 2, -1, 0, 100, 500. These are some of the scalar values that can be considered as a reward. So I'll give you some examples later on. But what happens here is the state, when the environment changes the state because of this action, the environment updates the agent about this state. The agent actually takes an action, but how agent is going to take that particular action? Because there are so many possibilities, right? There are so many possibilities, possible actions that can be taken. So how agent decides this action is appropriate depends on the previous experience, or let's say the reward that actually is shaped by the reward function. So agent receives all these rewards from the environment, and agent knows that, okay, this action is really good because I received a good reward. Or agent can, if in case receives bad reward, or let's say negative reward, then agent thinks that, okay, the action that I just took is not good one in this state. So agent will learn something from this reward. So reward is basically a very core concept of this reinforcement learning, how reinforcement learning actually works. And this is also a very important, very crucial part in RLHF as well, this ChatGPT, in ChatGPT also. So in many books, or in many textbooks of RL, you will see this figure, this figure. So this figure is exactly the same as this one. So here you have agent, you have environment, you have action, the state and the rewards are provided to the agent. But in some blogs or textbook, you can find this one also. You see, it's nothing different, not different than the previous figure. I'm just making you familiar with these figures. So in this figure, the agent is replaced by a robot. So you can think, if you are actually making a robot, really an RL agent, let's say, robot is an RL agent, let's say, then robot, in this skeleton, you can replace this agent by this robot figure, and then environment can be replaced with this globe diagram. Here, agent takes certain action, and then this environment provides you the state and all those rewards. And in some other blogs, you can find this figure also, and it's similar with the previous one. Here we have this globe as an environment, the Earth as an environment, and this robot is an agent. So the agent takes certain actions on this one. And sometimes you also see this figure as well. The agent is replaced by the brain, because brain is a very crucial part of, everyone knows, like brain is a very crucial part of our body, right? So, so in the RL system, the agent is the one who takes an action. In our body also, we decide something via brain, right? So brain decides something and we do that action. Similarly, in the RL agent also, RL system also, we have the agent does something. That's why agent is, sometimes you see this brain structure in terms of agent, and this Earth as an environment. But not only this one. You can see something like this in some of the research papers. So here, what happens? Let's see. Suppose somebody is trying to solve a problem. You see, somebody is trying to solve a problem related to energy. So we have energy system out here, and this can be considered as an environment. Okay, this can be considered as an environment. So we have an RL agent. It's a software system, let's say, that takes in certain actions on this energy, and this action will optimize the objective function. We call it objective functions. Later on, I'll talk about this objective function as well. Why we actually trying to solve that problem is basically we are trying to optimize something. If the problem is related to energy, we optimize energy. If the problem is related to finance, we optimize the finance, we optimize the cost. If the problem is related to game, we maximize the score, and that is actually optimization. So RL is really good in optimization problem as well. But there are so many challenges. Later on we can discuss that one separately. So this one is again the skeleton, where you find this part as an environment. So in this environment, you have like different things related to energy or electricity or something like that. Let me move to another example. This one is again interesting one. So here you can simply guess yourself. So the environment here is this board. You see, this is something by something board, I think, N by N board. So it's a board game where we have like a start point and destination. So this one is an environment, and there is this agent, and agent takes a certain action on this environment. So agent either takes up movement or right movement or down movement or left movement. So if, for example, let's say this agent is a robot, let's suppose. If this agent is a robot might be somewhere over here. Maybe somewhere over here, right? So, but what is the problem here? What the agent actually has to do is, agent has to move this road, let's say, and then finally come to some point, come to some target, terminal point, right? So, the job of the agent is to move. So, if the job of the agent is to move, then what are the actions that agent can take at any moment is, agent can either go up or right or down or left. If the robot is somewhere, agent is somewhere over here, it can go to left. So this is actually an environment. An agent is there, so agent takes certain actions. So once the action is taken, this environment changes the state, because initially probably the robot might be somewhere over here. And the robot takes action down, let's suppose, the robot moves down. Now there is a change in the state, you see. Then that one is updated to the agent, and it provides the reward as well. So in this case, what could be the reward? Reward is again a scalar value, probably moving down or left or right or up or down, probably receives 1 or -1. And when this robot actually reaches to the target point or the terminal state, let's say, then the robot probably gets, or agent probably gets 100. So agent always tries to get the highest reward. You see? So what I'm trying to explain with all these examples is that, so environment could be something like this. Environment could be something like this. Environment could be something like this. So it depends. If you are, for example, if we are talking about the autonomous vehicle, probably in that case, the environment could be pretty much something like this. Environment could be, the vehicles moving right on the vehicle itself, right or left, these buildings and all those roads. This is actually an example of environment. And what could be the agent? The agent is the car itself. The car has to go through, through the road without any accident. So that's the main purpose, without, destroying itself, or without destroying any other human being or any other things. So even in this case also, even in the autonomous vehicle system also, we can have this RL system, where you have this car as an agent and all these surroundings as an environment. And all these things happen even in this example also. I hope you understood the concept of environment and then agent. Now, I think with these examples, with all these examples, you should be able to visualize if you have any problem that is related to sequential decision-making problem. Sequential decision-making problem. For example, I'll give you one example. Suppose there is an inventory management system. There is the inventory management system. So in the inventory management system, a salesperson, let's suppose imagine that there is a small shop. A salesperson every day decides how much shall I order from the distributor so that I can sell to the customers. So this is a problem. How much shall I order? If I order more, then it will be lost. I mean, we'll be in a loss. If I order less from the distributor, then I will not fulfill the demand of customers. So it is not one-time decision, but the salesperson basically takes decisions each and every time. So that is a kind of sequential decision. So when there is a sequential decision problem, then you have to visualize that problem in this manner. Like, for example, this could be the environment and this could be the agent. And this agent can take certain actions, and the environment actually provides state information to the agent. So all these equations have to be aligned with each other so that we can easily solve the problem. For example, here, this example, this is the environment, like just now I mentioned inventory management problem, right? So in the inventory management problem, we have a different environment there. It's not like the autonomous vehicle system. You'll have a different environment, but the agent is there. And probably you might be wondering why there is this deep learning kind of thing, neural network, why there's this neural network. I'll come to this point later on, why this neural network is there and what is the role of this one. So here in this example also, we have the environment and we have the agent. Agent takes certain actions, observations, and then reward. Reward is there. So now I'll introduce some very common problem. When you go through the textbook of reinforcement learning, then there are certain problems that the textbook tries to explain to the readers. And they are, basically these slides are heavily inspired from the one developed by Fei Li. I think you have heard about her. Fei Li is a wonderful computer scientist in the field of machine learning. So cart pole problem. So now I am taking some very specific problems to explain this RL concept, okay? Very, very specific problems. So far, we are familiar with the RL skeleton diagram, right? We have this environment, we have this agent, and how they communicate with each other. Now, let me explain you a very specific, taking some very specific examples. So this is a card problem. Card-ball problem, where you have a very pendulum-like structure over here, and you have this card over here. This is a pole, this is a card, and there are wheels over here, okay? So the agent has to move this card horizontally, I mean on the left side or on the right side. You can only move on left or right. And the main objective of this one is not to make this pole fall down, okay? So what happens here is, if the pole is on this side, we have to move this card on the left so that this pole does not fall down this way. Or we have to keep this pole in the middle. It doesn't fall on the right, it doesn't fall on the left. But we can move this card on the left or right, you know, on the left side, on the right side. So the main objective is to balance a pole on top of a movable card. This is a movable card, so you can balance, you have to balance this one. So what is the state of this problem then? You know, it's a very challenging task. It's not that simple. You have a problem, and you must understand what are the states, what are the actions, what reward functions should be defined there to actually solve the reinforcement, to solve that problem using reinforcement learning, and it's really, really difficult. So with very simple examples like this, we will understand, bigger problems. So let me give you the state of this card problem. The state is the combination of all these elements. The angle, you see the angle, angular speed. What is the speed of this pole? Because if the pole falls this side, then it has certain speed. So the speed of the pole and the position, of course, the position, what angle, and horizontal velocity. That means the velocity of this pole, basically, the velocity of this pole. So with all these elements actually form the state of this environment. So in the card pole problem, this itself is basically an environment, right? So this is the state. And what is the action then? Action is you move this card on the left, so or on the right. So the action is either horizontal force applied on the left. So horizontal force, what force you should apply so that it remains in the balanced position. So that is the set of actions. And reward, you give one, you apply certain force, and it keeps in a balanced position. Then you get one, or the agent gets one as a reward. If it doesn't, balance itself and it falls down with this particular force, with this particular action, then you are going to get 0 as a reward. So with that 0 and 1 reward, the agent will learn, okay, this particular force is needed when the state is something like this. Are you getting my point? So in this example, what am I saying is, with this reward 0 or 1, the agent knows, okay, when the state is something, with this angle, with this angular speed, its position and horizontal velocity, we have to apply this force so that it remains, balanced, and then it receives reward 0. So with this reward, and the agent will learn something. Let me give you another example, so-called robot locomotion. This is another very, very popular example. And then I think you can do a separate project based on this one also. In this example, a robot is there. You see, a robot is there, and the major objective is to make the robot move forward. The robot is supposed to move forward. You see, it doesn't have to fall down. If it falls down, then you are going to get the negative reward. So what is the state then? So if this is the problem, then what is the state of this particular environment? The angle and the position of the joints. You see, there is this legs and then hands, all the joints are there. So the joints make certain angle. If all the angles of the joints, if they are proper, then actually the robot can move. So this state is very important to make this robot move forward. And then what is the action? Action is the torques applied on the joints. So how much torques you apply to the joints actually make the robot move forward. So this is the action. And reward is of course 1 at each time step, upright plus forward movement. So it depends on like how much movement you make. You can add that one and then you can add 1. So reward basically is up to you to define. But then this is very, very important and very, very challenging also. Many researchers actually work for the proper reward function. You have a problem, and what is the reward that is best suitable for this problem? It is really, really a difficult challenge. Now let me move to another one. So if you look at all these games here, sorry. So if you look at all these games here, what is the objective? You have to complete the game with the highest score. That is the objective. These are all Atari games. What is the state? State is the raw pixel inputs of the game state. For example, if you take this picture itself is, here in this example basically, this picture itself is a state. So with this picture, the agent knows where the ball is, agent knows so many other information from this picture itself. If you look at this one, the agent knows everything about this state, right? Agent knows about the state. So that is the state. What is the action then? Action depends on like, left, right, up or down in all these games. In all these games, the actions are basically a set of left, right, up and down position. And reward score either increases or decreases at each time step, right? So if the action is good enough, then definitely you're going to score the higher, you get the higher reward. If the action is not good, then you're going to get the lower reward. Let me explain you one more example. In the Go game, we already discussed about, I already mentioned this AlphaGo game as well. I think I suggest you go to watch. It is available in the YouTube as well. So AlphaGo is a very wonderful documentary. You shall watch that documentary as well. So what is the objective of this Go? The objective is to win the game. And what is the state? Position of all pieces. So for example, this, you see this white pieces and then black pieces. This part whole can be represented in the matrix form. So the matrix form itself is the state of this game. So in the action, where to put the next piece down. So if the player is supposed to put the white piece, then the action is where to put that white piece is actually an action. And the reward, 1 if win at the end of the game, 0 otherwise. So that could be the reward. So I hope you understand the basic concepts of reinforcement learning, right? The overview of reinforcement learning. And I hope you also understood what are the states, what could be the actions, what could be the reward, and what is the major objective of that particular problem. Now let me discuss about Markov decision process. In short, we call it MDP. So MDP is a mathematical formulation. You see, mathematical formulation of RL. So now what I usually do is, whenever I want to solve a problem P using reinforcement learning, I try to map this problem into MDP. If I map this problem into MDP, then it will be easy for me to solve this MDP, using the reinforcement learning. Once you solve the MDP using reinforcement learning, then you are done with the problem, the bigger problem itself. So it is very, very important when you talk about reinforcement learning, there are so many concepts we need to understand. For example, dynamic programming. I will not talk about dynamic programming, but it is better to understand what dynamic programming is to understand the reinforcement learning. right? So similarly, Markov decision process, MDP in short, is also a very important concept here. So in MDP, I think these symbols are very familiar if you are aware about MDP. So MDP actually is a tuple, a tuple with the 5 elements. But what is MDP? MDP is a mathematical formulation of reinforcement learning problem, and it's really interesting, to map the problem into MDP. And it always follows the Markov property. It should always follow the Markov property. Every state has to follow the Markov property. What is Markov property? Markov property is the current state completely characterizes the state of the world. What does it mean? It means that any state, you see, that any state in a game, let's say environment, or any state in an environment does not depend on the history, previous past states. So that is what the Markov property basically is. So in MDP process basically is defined, as I already mentioned, with the 5 elements. It's a tuple of 5 elements. The first S, A, R, P, and then gamma. So S is a set of possible states. You see? Now you can think of a game Go, and you can imagine how many states will be there with a simple Go. Let me give you another problem, another game, tic-tac-toe. Imagine tic-tac-toe. It's a very short game, right? But then you can think of all the possible states. It's very big, in fact. So even other games like Ludo or any other games like card games, you see, those have thousands and millions of states. Possible states are there, and that can be represented as S. A is a set of possible actions. In the example of Atari games, what were the possible actions? You can move up, you can move right, you can move left, you can move down. Right? These 4 is actually form a set of actions. R is the distribution of the rewards. So how much reward? How much reward we're gonna get by the agent? For example, if you take certain actions, then it gets 0, probably 0, or probably 1, or -1 probably, or 100. So then -1, 0, 1, and 100 actually form a reward. Transition probability. Well, I will not be talking more about the transition probability in the later slides, but then I will explain a little bit about transition probability. For example, you have one state. You think of any problem possible. So there is one state. We take certain action, then we change the state of this environment to another state. So what is the probability of moving from this state to another state is what we call a transition probability. So there is always, not always, basically in the model, there are like 2 RL types, like model, when you talk about model, we have like model-free and model-based RL algorithms. So if you are using the model-based algorithms, there is always a transition probability. There is always certain score, probably 0.5 or 0.6. There is a probability from moving state 0 to another state 1 or another state S2. And this is a discount factor. I will come that later on. Why this discount factor is very important. So let me take one very simple example. This is a grid example where you have like 1, 2, 3, 4, 4 by 1, 2, 3, 3, and these are two positions where you can reach. So if there is a robot or if there is a human moving from all these these cells, so it is supposed to move from any place to this or to this position, then the agent will receive some reward. So if some robot or human being is in this cell, for example, let's say, if we place human in this cell, then what are the possible actions then? It can move up, it can move right, it can move left or down, and it can move left. So these 4 elements actually form a set of actions. So if grid example is considered, then this actually is the state, this actually is the actions, and reward can be minus 1 if it does not reach to this one. Or the reward can be 10 if somehow the agent reaches to this point, or the agent reaches to this point. For example, if the human being is, for example, agent, whatever, agent, let's say agent is somewhere over, it moves this direction, let's say, and then finally reaches to this location, then it's going to get very high reward because our objective is to reach to this point. So this is one example of, we call it like very simple grid. So if you consider a grid, general grid, something like this, then there are so many possibilities. Now I'm introducing you this new word called policy. What is policy? So if imagine that a human or agent is somewhere over here, it can move any direction. It doesn't know where to go. It knows like it has to reach to this point or this point, this location. But it doesn't know how to reach to this point or how to reach to this point. And we train this agent, we train this agent using RL concept, RL algorithm, and we finally come up with this solution. Let's say, if the agent is somewhere over here, then it can go up. Over here, it can go up and it reaches this point. So this is what we call a policy. Policy is basically a sequence the agent takes, over the certain period of time, the agent takes certain action in that particular state, and it gets the reward. And it takes another action in that another state, and then it gets reward, and it takes another action. So this, there is this whole sequence, and that is what we call a policy. So, and then we need to find out, the major thing is, when we actually, what is the meaning of solving any problem using RL then? The main concept of solving a problem using RL is to find the optimal policy. You see, to find the optimal policy such that we maximize the reward. Right? Let me repeat once again. What is the meaning of solving any problem using RL is we try to find out the optimal policy, so that we maximize the reward. So every time it gets the reward after certain action, we add all those rewards, let's say, and we sum them up. When we come up with a single reward, we have to maximize this reward. You see, and that's the solution of the optimization problem. Now let me introduce few more concepts. But how do we do this one then? Then we have this concept called value function. You see, value function, and there are two types of functions, value functions. One is state value function, and there is this action value function. Now, what is it? Now, I request you to imagine. Let me turn this one. I think yeah. Now let me request you to imagine there is this grid. Okay, grid word. Grid. So I'm in one cell. Let's say I'm in one cell. Now, what are the actions that I take from this position? This state is I can move right, or I can move left, or I can move up, or I can move down. So there are 4 possibilities I can take as an action, right? So now, if I move to the right side, let's say, after taking certain action, I move, my position is somewhere over here. Now this is again the state, right? But how good this state is? So there is this function, we call it state value function, that actually measures the goodness of this position. You see, there is this grid over here, but how good it is to be in this state. So this is basically a function. This is basically a function that measures the goodness of this particular state. But how do I understand this goodness then? Goodness is basically, this state is good if it actually tends to, make you reach to the final destination. You see, that is the main objective. And what is this action value function then? Action value function is little bit different than this value state function. State value function. For example, I'm in this position, let's say. I'm going to take next move, that is next action. So if I take this action, let's say, if I take this action, how good this action is, based on this state, how good this action actually is. So that actually is described by action value function. So you try to understand the difference between these two values, okay? State value function actually describes how good it is to be in this state, okay? And then this action value function actually describes how good your action is based on that state. So these are two different things, but then the calculation is pretty much similar. So if you look at this equation, I will explain this. Now let me move to this equation, a very simple equation. So this RT actually is the reward, total reward, you see? And the summation actually gives you that meaning. So if you add all these rewards, then you get some value. This is the expected value, basically expected value over all the possible rewards. So now let me explain it. Like, now let's suppose I'm in this position. In the grid system, I'm in this position. I take an action, the state changes. I was there before, but right now I'm here. The state changes. But I get the reward, right? But once I'm here, I'm going to move to the next state also. So this phenomena continues till the end of the game, or till the end of the episode, let's say. So once you reach to the end of the episode, you're going to get reward now and then. I mean, in every step, you're going to get reward over there. So, but the problem is, the reward that I immediately get after this action is more valuable than the reward I'm going to get in the later stage. Getting my point? So, let's suppose I'm in this state. I move to the next state. I get the reward because I moved the action. I mean, I took an action. So, I get the reward. But then I'm going to get other rewards in the future also, right? So, we sum them up. But the thing is, the immediate reward is more valuable than the rewards that we are going to get in the later stages, because you don't know where you will be in the future, right? So that's why this discount factor is there. Discount factor actually makes this reward decay. You know, so the immediate reward is more valuable than the future reward. That's why this discount factor is there. So when you sum them up, your discount factor, this t, when t equals to 0, this discount factor is 1. When t equals to 1, a discount factor, if for example this discount factor is 0.9, then the equation becomes pretty much, I think, it will be clear later on, let's say. So this one basically gives you the state value function. Similarly, the action value function, the equation for this action value function is something like this. If you look at this one, so you have the state S naught, and then you move to another state. You have an action, you take the action following the policy pi. The policy basically is represented using the pi value. So this is the expected value. So this is again a same principle. We follow the same principle to calculate the state value function and the action value function. So once you have these functions, then we are ready to dive into the Bellman equation now. Now let me briefly describe what a reward is. Reward is basically a scalar value. I've already mentioned this one. The reward is very important factor in RL. So I quickly move into the next one. So now let me consider a grid problem again. So here it is a collection of rewards, you see. The immediate reward is also there. The delayed rewards are also there. When you sum them up, then you have this GT. This is a total reward. So if you expand this equation, then it becomes R, T plus 1, gamma R, T plus 2, T plus 3. T actually represents the time step, okay, time stamp. So as you move on, it continues. But then again, RL has like two types of RL. You have like episodic and then continuing. Continuing, this is an example of continuing. But then in episodic, we have a finite number of timestamps, okay? You have a finite number of timestamps. You can explore more on these two things, episodic and continuing. So this is the total reward expanded in the expanded form. So if you if you look into this equation, then we can rewrite this equation with this one. Gt equals RT plus 1 plus gamma G T plus 2, T plus 1. This is for the Gt at the timestamp T, you have the sum of RT plus 1. RT plus 1 actually is the immediate reward. Okay, but this one is actually a delayed reward. That's why this gamma symbol is there. The discount factor is there because immediate reward is more valuable than the future rewards, delayed rewards. So you have these equations. Now let me derive these equations then. If you consider, now let me consider this once again. Let me move to this equation. Now if you look at this one, you can replace the GT in this equation, and you will have this equation. You see, and now you immediately realize that this GT plus 1 can be written as VST plus 1 because it's the next state value function. So when you have this equation, if you look at this equation, you have kind of, you already have a feeling that, okay, there is this, we need to calculate VS, but before calculating VS, we need to calculate VST plus 1. So this is what we call a recursive definition of a value function, right? So in RL also, there is this kind of recursive definition. So before you calculate the value of Vs, S is like any state, then you have to calculate the value of this one. So this actually is what we call the Bellman equation for the value function. Right? Similarly, you have this equation, like in the first slide, I think I showed this equation. This is a Bellman equation. This is a Bellman equation for the Q value function. It's an action value function. So here you have this reward over here. You have this QS prime, A prime. You already noticed that one. To calculate this one, you have to calculate this one. But then this maximum value is there. Because of the algorithms. This is again a recursive definition. Now, let me move to a very, very important topic of RL, under this RL. This is so-called exploration and exploitation. Okay? Now, let me take you to, again, I think we have half an hour left. Jatin, where is it? Jatin, half an hour left? 20 more minutes. Okay, 20 more minutes. Let me move quickly. So now let me take the grid example again. Let me explain what is this exploitation and exploration. So if we now imagine in the very beginning, I don't know the value of this state. So how do I calculate? I just explore the thing. I just move to the next level, next state. Or I can move to the another state. So this is what we call exploration. I don't know exactly the result. I don't know exactly the reward. I don't know how much I'm going to receive that reward. But I simply move because I hope it will lead to the higher reward. You see, the agent, in the problem, the agent can take action, but it doesn't know whether that one leads to the higher reward or not. So that is what we call, this phenomena is what we call exploration. But what is exploitation then? The exploitation is when agent already has the information that this particular action is better or good, or agent already knows that this particular action will lead to the higher reward, then what agent is going to do is, agent is going to take this action because it knows that it is going to receive the higher reward. And that is what we call exploration, because the agent always has, at any instance, agent has 4 possible actions it can take, right? But why it is taking the left action is because it knows that this is going to receive the higher reward. That's why it is actually exploiting the scenario. It is exploiting the scene. So that is what we call exploitation. But then again, exploitation and exploration is a trade-off. Why I'm saying trade-off is because we have to keep in mind when RL actually, in the beginning, RL doesn't know any values, right? So it has to explore. But once explore, then it can go to the exploitation, you see. But then again, there is a trade-off between exploitation and exploration, because too much exploitation can lead to suboptimal policies. You see, if you do not explore, it is not going to get the higher reward. So exploration is also important, exploitation is also important. I'll give you some more examples. Let's see. For example, restaurant selection. What do? In Tamil or wherever you go, you exploit, or you either exploit or explore. Those two things are always important. So exploitation is go to your favorite restaurant. All the time you go to the favorite restaurant. That is what we call exploitation, because you know the food, right? What is exploration? Let's try something new. Probably that new restaurant may be better than the one that I used to go. That is what we call exploration. In RL system also, the agent exactly works in this fashion. Exploration and exploitation, but you have to balance these two things, right? So I give you a few more examples. Online banner advertisements. What is the exploitation? Show the most successful advert. Always show the most successful advert. That is exploitation. What is exploitation? You show a different advertisement. Oil drilling, drill at the best known location to get a lot of oils. Exploration, you drill at a new location hoping that you're going to get something better. But it is possible that you may not get the better result as well. That is possible. And game playing, exploitation, play the move you believe is the best. And what is exploration in this case? You play an experimental move. You take a move, something very different. You have never done that before. You don't know whether it's going to get the higher reward or not. So these are some of the examples of exploitation and exploration. And in every RL, whenever you implement any problem solution, then you have to think of this exploitation and exploration, and you have to take a very good measure, because there are certain algorithms. For example, epsilon greedy algorithm is there to address this exploitation and exploration mechanism, trade-off. And there is another algorithm called Thompson sampling. There is another algorithm called UVC. So all these, some very good algorithms are there to address this exploration and exploitation. But again, let me mention you that this exploration, exploitation is a trade-off. So you always have to balance, you have to balance. So now understanding all these things, now let me quickly move into the RL algorithm. This is what we call Q learning. Q learning is very popular. That's why I just want to, just for the sake of the name itself. So I'm including this slide. In this RL algorithm, you simply repeat all these tasks, basically. What you do, you create a table, probably a matrix, and in each cell, you calculate this value. You see, you remember this QSA. QSA is the state action value, right? How good this particular action is in the context of state. So you calculate this QSA, and then you store this QSA value into this table. And this table basically in the Q learning algorithm is called Q table. Q table. And in the Q table, you have this two-dimensional Q table, and in each cell contains this value. But how are you going to update this value? You train the agent. You train the agent with the environment, within the environment. You train the agent, this RL agent, and you use all these equations. This equation is very important to update the value QS, A itself. So with this value, your RL agent will be well trained. And when you deploy that well-trained RL agent, that is how it is going to take the action in any context, in any scenario, is it looks into the Q table, and it looks into, it understands the state. So which action is better in that state, it takes that value. It takes the highest value, and it takes that action, particular action in that context. So it's a very simple Q learning algorithm. So if you are really want to dive into this RL field, I suggest many of you are, I think, students. I suggest you first implement Q learning algorithm, because you have all these terms and terminologies familiar. you are familiar with all these terms and terminologies now, I suggest you implement Q-learning algorithm. Once you understand Q-learning algorithm, it is really easy to understand deep reinforcement learning as well. And it's a very powerful concept as well. Deep reinforcement learning, what happens in deep reinforcement learning is, as I already mentioned, you have this reinforcement learning, right? So how do we maintain all those values? So far, we maintain the Q table. We maintain the table. It's in the two-dimensional form. We maintain the table, and this RL agent is trained. We fill up all those tables, basically. So what happens in deep reinforcement learning is we do not use this Q table. We remove this Q table, and the RL agent basically will be replaced by this neural network itself. So in basically so far what we have studied is in Q learning algorithm, let's say, we maintain the Q table. You have the state, you have the action. You look this state and actions, and you find the highest value somewhere over here, and you take the Q value. You get the Q value. But in deep reinforcement learning, what happens is you only take the state as an input. So once the state inputs, this neural network is well trained, and it provides actually different Q values for each and every possible actions. So out of this one, which one is the highest Q value, you will perform that action. You see? So in deep reinforcement learning, what happens is basically you use deep learning, basically in the RL agent. In the previous slide, you have this brain kind of thing there in the RL skeleton, right? So in the brain, in Q learning, the brain used to be a two-dimensional table where you have like state, value, action. All those values will be stored, right? But in deep reinforcement learning, the brain is replaced by deep neural network. So basically, this reinforcement learning is very, very powerful, very, very efficient in comparison to Q-learning algorithm. So you have different algorithms like DQN, right, Rainbow, and PPO algorithm is also a deep reinforcement learning algorithm. So these are very powerful algorithms. You can make use of it. So let me quickly, I think I have a couple of 10 or 15 minutes more to discuss this reinforcement learning from human feedback. Now, why now this reinforcement learning is with ChatGPT? Why ChatGPT is trying to integrate reinforcement learning? Otherwise, this ChatGPT, or let me say LLM, okay, instead of ChatGPT, let me say LLM. Why this LLM was not into RL? It was like supervised learning, unsupervised learning. LLM was, trained with all these items. Paradigms, but not with RL. But now, ChatGPT is using this one, and many other LLM algorithms are using RLHF. But what is it? Why do we need this one then? How does it work? Let me briefly give you this example. So human feedback in AI system is very, very important. Very, very important. But don't. I don't want you to think again like human feedback also destroys the AI system. No, probably not. We can maintain that one within the system. But then to become a better AI system, it can take some feedback from human and improve itself, right? So ChatGPT actually does that one. I think many of us use ChatGPT. So if you have a question, if you put some question, or if you give a prompt, let's say, then it's gonna, sometimes ChatGPT provides you two options and ask you to, I ask you to select the best one, and you select that best one that suits you, right? So that actually is a feedback to ChatGPT. That actually is a feedback to LLM. So that is what we call that is what we call human feedback. But what is this reinforcement learning human feedback is? How does this LLM, let's say, uses it? It has these three stages. So the first one is called language model pre-training. The other one is called reward model training. And this is actually the heart of RLHF system, reward model, is the heart of this RLHF. And finally, you fine-tuning fine-tuning with RL. Now let me briefly go into each and every step, right? So the first thing is, of course, you have this language, initial language model, the first one, without RL. There is no RL at all, right? So this can be trained with the prompts and all other, these, what do you call it, text data sets and all those things. Human intervention it's not required. But then again, there is this initial language model, trained by all this information. So now what happens is, so once the prompt is given, this is going to give you the output. The output is actually the sequence of tokens, right? Output is actually the sequence of tokens. And then LLM asks you to choose which one is best. It provides you the options, okay? It can even, that is only the, I think, I came across this process, but there are other ways to give the feedback. Basically, the Likert scale, I think you are familiar with. Likert scale is there, other thing. There are other processes, other phenomena are there where you can give the feedback to the system, AI system. But in ChatGPT, it provides you two options, and then you have to select one of them. So once you have this, once you have all these feedbacks, you're gonna manage the system. Actually rank all these inputs. What are these information? These informations are, for example, there is a prompt given to this initial language model. It gives you the output, and this output is rated by the user, human being, right? By the user or client. So all these informations will be collected, and this collected information actually is being used to train a reward model. This reward model actually is another entity where, with all these ratings, with all these rankings, this reward model is well trained. So this reward model is basically the heart of this RL system. So if you look at, I have few text over here, and once this information, this input is given, this model actually gives you a scalar value, and that is equivalent to the reward. Okay, so this reward, if I consider this, let's say R theta, let's say R theta, so this actually gives you a reward. So if you are familiar with this thing, then let me move to other one. Okay, so this reward model actually is based on the transformer, of course. It's a deep learning model, and we have a very variation in sizes relative to policies, and all. This text is actually the input, and this reward is basically the output. So based on this reward model, if this reward model is well trained, then we include this reward model in the system to fine-tune this ChatGPT. How it actually works, let me quickly explain this one within a couple of minutes. So we have this initial language model, and you have this, you have this fine-tuned language model with the ratings, all these ratings. So this output actually is provided to the reward model, and reward model actually provides you the reward. So this reward, basically, the major portion of fine-tuning is to minimize the loss function. And this loss function basically is a loss function that belongs to PPO algorithm. So what is the loss function basically? Is, let's suppose we have a reward from another, we have the original reward, let's say 10. Suppose, just give you a simple example. And let's suppose we received a reward of, let's say, 5 from another model somewhere over here. We have 5, and then the original is 10. And what is the difference? The difference is 5. So we want to reduce this difference between the original reward and the predicted reward. So, and that is done by the PPO algorithm. And introducing this PPO algorithm in whole system basically is RL within the ChatGPT. So this is how PPO algorithm is being used. So PPO algorithm is used to reduce, to minimize the loss function, to customize the loss function. So with all these things, you have this ChatGPT, with the human feedback, but then again, you need to study a very few couple of things also. For example, in this implementation, you have the KL divergent concept also, and that is very important concept as well. So, but then for now, these are some of the steps that ChatGPT basically follows. But now there is another algorithm, so-called DPO, and by introducing this DPO is not related to reinforcement learning. So DPO is actually helpful in LLM to even bypass this PPO concept, PPO algorithm. So DPO is really getting popular these days. So RLHF is there, but without RLHF concept is there, but with the DPO concept, DPO algorithm implemented. So basically, this RLHF is a very important, because it actually fine-tune the response produced by LLM. How does it fine-tune that things? Because it fine-tunes because of the human feedback. Human feedback, why human feedback? Because human feedback is used to train the reward model. So this reward model is well trained with the human feedback, and based on this reward model, the system overall calculates the reward of each response. It tries to maximize that reward, it tries to maximize that reward. So with all this information, I want to conclude with these great pictures. I really appreciate all of them. These are some of the great contributors in the field of reinforcement learning. Please remember their name, Satan and David, and then Sergey, and then the other guy with the I forgot his name. But then again, these are some of the great personalities that you don't want to miss them with all those papers, He's the one, I think, who introduced PPO algorithm. He's the one who developed PPO algorithm. David Silver, I think you heard about AlphaGo, right? He is credited for that one. Satan, he's the one who actually laid the foundation of reinforcement learning. Trial and error concept, temporal difference, all this concept, actually, he's the one who explained us. I mean, via this book, basically. And for you who is really into this reinforcement learning system, I suggest you go to this reinforcement learning book. This is actually a Bible for us. And thank you so much for listening me. And yeah, let's go for the QA session. I think it's quite long session, one hour, 30 minutes. Yep, there is. Yeah, I can see some.
And it doesn't have information about the previous states or actions. What is it going to do? Like if the same actions outside the QA.
Okay, very good question, in fact. Suppose the agent is, let's suppose there is a queue table. Initially, the queue table is filled with 0, for example, or let's say -1 or something like that. So initially what happens, the agent doesn't know where to go, where to move, because it doesn't have all those values, right? All those values ready. So it actually explore. Always it explore the thing. So it randomly moves. It takes random actions. So you select, out of 4 actions, you select one of them and you go on. You continue with that one. But it is going to give you certain values after that one. So initially, the exploration timing is really big. You see, you explore a lot. But as the time goes on, the exploration rate will decrease. So probably after so many time period, there is at some point you do not need to explore at all. You just exploit them. You got my point? So that's why this exploration and exploitation is a trade-off. It's a very important concept. So in the beginning, we have to explore. Yeah.
Thanks for the presentation. So I need some clarity between model-based and free-based reinforcement learning versus negative and positive reinforcement learning.
Can you repeat? Sorry, can you repeat the question again?
So I
Difference
think,
between
very difference
between
model-based and free-based reinforcement learning
okay.
versus positive and negative reinforcement learning.
Okay, thank you for the question. Well, model-based reinforcement learning and model-free reinforcement learning, these two things are very important because whenever you try to solve a problem that can be solved, you will first see the problem. And if it is like sequential decision-making problem, we go for that. We go for the RL. And we try to map that problem into Markov decision problem, right? So, but there are different kinds of problems. So in one type of problems, what happens is you have one state and there is a probability. When you take a limit, actions are always, most of the time, actions are always limited. But in some cases, states are very, very large. But the action is always limited. So with the limited actions, if you take one action, if you take one action, then it's going to change the state of that environment to the another state. From, let's say, from S0 to S1, let's suppose. So, but what happens in the reality, in the real scenario is that there is always a probability of having this action and changing that state from S0 to S1. For example, taking this action changes from S0 to S1 is 0.5. Let's say there is a probability. And there is another probability with that action changing from S0 to S2, another state. So if there is like well-defined probability, then we can have this transition probability also well-defined in the Markov decision process. So if your problem is very similar to that kind of things, where you can have a probability of moving from one state to another, then we basically use model-based algorithm, model-based reinforcement learning. Then we follow that one. Otherwise, if there is no probability from moving from S1 to S2 or S2 to S3, there is nothing like that. There is no probability. It depends more like what do you call it? Stochastic nature. If the environment is like stochastic in nature, then you will probably follow model free because you do not know what is the probability of moving from one state to another state. So in that case, we have to use model-free reinforcement learning. For example, in the inventory management system that I explained, what happens, we do not know what is the customer demand. At any given time, we do not know. We only know what demand was there in the last day or previous to that day. So we do not know the demand of customers, like how much items I will be selling today or tomorrow, right? So in that case, the environment is pretty much stochastic. We don't know. So if you want to solve this inventory problem, then it's a good idea to follow model-free reinforcement learning algorithm. And regarding the next question, it's negative, positive. I'm really sorry, I haven't heard about that negative or positive reinforcement learning. If you can, maybe we can discuss that later on. You can explain, the question a little bit more, and then we'll talk that later on. Yeah.
Could you also share your thoughts on current trends in inverse reinforcement learning and imitation learning? Specifically, in what type of problems or scenarios are these approaches better than traditional reinforcement learning?
Thank you. Great questions, by the way. Yeah, reinforcement learning. When we think of reinforcement learning, it's really, really difficult in many ways. The one is basically sample inefficiency. We say that reinforcement learning is not good in terms of sample efficiency, and training takes quite long time, and there are other many more challenges are there. But then again, in the beginning, when RL was booming, we only notice that reinforcement learning is good for gaming. And if it is only good for gaming, then what is the purpose of having reinforcement learning in the real world problem, right? So, but then later ChatGPT started using it, and a few other fields are also emerging, probably in the field of you see, in the field of education, in the field of healthcare system. RL is really doing great in this one. Because why? Because there are so many concepts evolving, like inverse reinforcement learning, imitation, or we call it transfer learning also, right? Transfer learning systems are also there. So let me give you one example. Basically, in the field of education, probably we could use this RL human feedback concept as well. So nowadays, I personally, in this today's talk, I personally gave a talk on some examples mostly related to gaming, because gaming examples are very easy to understand, because we feel like, we feel like playing games, and it's really easy to understand the concept. But then the applications of RL is really spreading in other fields as well. Like I said, in the health informatics and in the healthcare, and even in the education system, in every other field. So this is a very good question, and a vague question, I personally believe. But then, yeah, we will definitely see a lot of applications in other fields as well, not only in gaming, mostly in the field of robotics. So it's gonna, RL is really doing great job in the field of robotics as well. And in terms of robotics, you will be applying a lot of transfer learning, a lot of imitation learning, right? So I hope like these fields will be very in a good position with this reinforcement learning algorithm. I mean reinforcement learning paradigm. Yes. Thank you very much. Yes. Hi, Jitin. Shall we stop now? Okay. Thank you so much. Thank you, Jitin. Thank you so much. Thank you so much to all the participants. I hope somehow I managed to talk about a little bit about reinforcement learning and RLHF itself, right? And I'm really amazed to see all of you so enthusiastic about this AI, ML, and RL systems. I wish you best of luck, and thank you ANSI team and including Nami also. PCS Kanal, I don't see him here. Is he around? Dandapani sir also. I especially thank to Dandapani sir as well for this opportunity. Thank you so much. Thank you all. Thank you. Enjoy the day. Hello everyone. My name is Manoj Shakya. I'm an assistant professor at the Department of Computer Science and Engineering. My field of interest is machine learning. More specifically, I can say reinforcement learning is the one that motivates me to work on. And recently, I completed my PhD from Nanyang Technological University, NTU, from Singapore. And during my PhD work, I mostly work on the reinforcement learning. So today, I had this opportunity to give a lecture on this reinforcement learning, basically. And there were a lot of fantastic participants. And after my lecture, I found that many of them are really enthusiastic about learning reinforcement learning. Because when I talk about reinforcement learning, many people, they don't basically even, think of implementing this RL. But I found some of them are already implementing reinforcement learning in their project, in their company itself. So it was really a fantastic experience. And the program, the event, so-called ANAIS, organized by NAMI, is a fantastic event. I really enjoyed being here. It's really an honor, in fact. And I'm very thankful to NAMI itself. because what I realized is that many participants, mostly students, they are benefiting from this event in the perspective that they came to know about what research basically is, what research in AI basically is about, and the resource persons that AIS is gathering is wonderful. It's not that simple to have this wonderful event, to gather resources from all around the world, including US, South Korea, within Nepal itself, and India, and other countries. And participants are also wonderful. Most of them are definitely from Nepal, and some of them are also from the other countries as well. And I hope that they learn not only about the reinforcement learning, not only about the supervised learning or computer vision or any particular field, but they also learn about how the networking is done, how the research is basically done in company or in the university, academia. And most important, this platform actually is providing a very good opportunities for all the participants to have this wonderful networking. Organizing this event is very challenging, especially in the country like Nepal. And to motivate students in this particular area is another challenge. But then ANAIS program as such is very important in different aspects. Most of the students, they have this program like AI program or ML programs in their curriculum, but they do not have an opportunity basically in the field of how to organize or how to go through these research activities. In my opinion, this event actually facilitates all students to move forward into this field, not only in getting the lecture, but also in having the research flavor or having the network with very expert personnel, expert researchers. So in my opinion, I believe that this event is not just an event. It is, in fact, a wonderful opportunity for all the students. What I realize is that this kind of event in Nepal is a rare event. It is very rare in terms of the resources, in terms of the knowledge creation, in terms of networking. You will not find this kind of event happening many in Nepal. So I strongly suggest the prospective participants or prospective students to join this program if you are really interested, if you are really enthusiastic about doing research, conducting research in the field of artificial intelligence, in the field of deep reinforcement learning, because conducting research in this field will be very, very impactful to the society, impactful to the Nepal as a whole, impactful to the world as a whole. That's why this event has a very tremendous impact actually for all of us. So I strongly suggest you that you go for this event and you improve your research skills, you improve your networking, you improve your knowledge in the field of artificial intelligence and machine learning. Thank you very much.